Welcome to this video on zk-SNARK, one of the most powerful cryptographic technologies developed in recent years. zk-SNARK stands for Zero-Knowledge Succinct Non-Interactive Arguments of Knowledge. This breakthrough in cryptography enables us to prove we know something without actually revealing what that something is. Throughout this video, we'll explore how this fascinating technology works and why it's becoming essential for privacy and security in the digital world. Let's break down what zk-SNARK actually means. The letters zk stand for zero knowledge, which means proving something without revealing any information. The letter S represents succinct, indicating that the proofs are extremely small and fast to verify. N stands for non-interactive, meaning the proof can be verified without back-and-forth communication. R represents argument, which refers to the computational soundness of the proof. Finally, K stands for knowledge, emphasizing that we're proving knowledge of specific information. Together, these properties create a powerful cryptographic tool. At the heart of zk-SNARK is the concept of zero-knowledge proofs. Imagine being able to prove you know a secret password without ever saying what the password is. That's exactly what zero-knowledge proofs allow us to do. The prover can convince the verifier that a statement is true without disclosing any information beyond the validity of that statement itself. This means you maintain complete privacy while still providing mathematical certainty that you possess the required knowledge. It's a revolutionary concept that changes how we think about proving information. Every zero-knowledge proof system must satisfy three fundamental properties. First is completeness, which guarantees that if a statement is true and the prover is honest, the verifier will always be convinced. Second is soundness, which ensures that if a statement is false, no dishonest prover can trick the verifier into believing it's true, except with negligible probability. Third is the zero-knowledge property itself, which means that no information is leaked beyond the validity of the statement being proven. These three properties work together to create a secure, reliable, and private proof system. One of the most impressive features of zk-SNARK is their succinctness. The proofs generated are incredibly tiny, typically just a few hundred bytes in size, regardless of how complex the underlying computation is. This means you could prove that you correctly executed a computation involving millions of steps, and the proof would still be remarkably small. Even more impressive is the verification speed. These proofs can be verified in just milliseconds, making them practical for real-world applications. This combination of small size and fast verification makes zk-SNARK incredibly efficient. The non-interactive nature of zk-SNARK is a game-changer for practical applications. Traditional proof systems often require multiple rounds of communication between the prover and verifier, sending messages back and forth. With zk-SNARK, the prover generates a single proof and sends it to the verifier. That's it. No further interaction is needed. This proof can then be verified by anyone at any time without needing to contact the original prover. This property makes zk-SNARK perfect for blockchain applications and other scenarios where continuous interaction isn't feasible. The zk-SNARK process involves three main phases. First is the setup phase, where we generate a proving key and a verification key using what's called a trusted setup. These keys are specific to the computation being proven. Second is the prove phase, where the prover uses the proving key along with their private inputs to create a proof. This proof demonstrates that they know certain information without revealing it. Finally, in the verify phase, anyone can use the verification key to check whether the proof is valid. This three-phase structure makes the entire system both secure and efficient. Understanding zk-SNARK requires familiarity with four key components. The circuit is a mathematical representation of the computation being proven, essentially translating the problem into a format that can be processed cryptographically. The witness consists of the private inputs that only the prover knows. Public inputs are pieces of information that both the prover and verifier can see. Finally, the proof is the cryptographic data that validates the entire computation. These components work together to create a complete proof system that maintains privacy while ensuring correctness. zk-SNARK are already being used in numerous real-world applications. In cryptocurrency privacy, they enable private transactions in blockchains like Zcash, where transaction details remain confidential. For blockchain scalability, zk-SNARK power Layer 2 rollups, allowing thousands of transactions to be processed efficiently by generating a single proof for an entire batch. In identity verification, they let people prove credentials like age or citizenship without revealing personal data. For voting systems, zk-SNARK enable anonymous yet verifiable electronic voting, ensuring election integrity while protecting voter privacy. These applications demonstrate the transformative potential of this technology. zk-SNARK represent a cryptographic breakthrough that enables verification without revelation. They allow us to prove knowledge while preserving complete privacy. The combination of compact proofs, instant verification, and zero information leakage makes zk-SNARK an essential tool for modern privacy-preserving systems. As we move toward a more digital future, technologies like zk-SNARK will become increasingly important for protecting our privacy while maintaining trust and security. This powerful cryptographic technique is changing how we think about proving information in the digital age.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.